Chapter 15, Solutions. I wish this chapter was solutions to my personal problems, but alas, it's a different kind of solution. So there's a little preview. We're not going to cover all of that. So in chemistry, what is a solution? A solution is a homogeneous mixture. Okay, we talked about mixtures and homogeneous, heterogeneous before. So just a reminder, a mixture can vary in composition. It's not always the same. And homogeneous means that the two components of the mixture or more components are distributed evenly throughout. So there's no layers or chunks or anything. So in a solution, there are two basic parts, the solvent and the solutes. So one way to identify which one the solvent is that it is the substance present in largest amount. So whatever there's more of, the majority, that's the solvent. Anything else that's in there is considered a solute. That's one way of defining it. If we talk about an aqueous solution, aqueous means water. So an aqueous solution has water as the solvent, always. There are many different types of solutions. So you can have a solution that is a gas that is a solution of two gases. And we are breathing that right now. We call it air. Natural gas that comes out of the little jets and that we light to get heat from the Bunsen burners. That is a mixture of different gases. Okay? So you can have mixtures of gases. You can have a gas dissolved in a liquid. An example of that is carbonated water or soda water. It's got carbon dioxide dissolved in the water. You can have two liquids dissolved in each other. Two liquids, the solute and the solvent both being liquids. Examples here are vodka in water or antifreeze in water. Antifreeze is ethylene glycol. It's a liquid. It's not actually that bright green. They put that in there to alert you to its presence. But you mix that. Makes you want to drink it more. Yeah, don't drink it. I mean, it's a pretty color, but yeah.
Brown would be for me the color.
Yeah, make it the color of poop or something, right? I have 6 children. I was roused from bed the other night. Mommy, come wipe my bottom. Yeah, so. And that reminds me of a joke. What's brown and sticky?
Mousetrap.
A stick. Those are called unjokes. Anyway, so you can have unjokes or non-jokes. I forget the name of them. Okay, what am I doing here? I'm pressing the wrong place. I'm not distractible. Have you seen any squirrels lately? So liquid and liquid, you can have, probably the most familiar type of solution is a solid solute dissolved in a liquid. And these are things like seawater, sugar dissolved in water. This, drink I have is red food coloring dissolved in water. That's the main ingredient, I think, is red food coloring. You can also have a mixture of two solids. Okay?
Huh?
Yeah, right? Huh? Thank you. So
Flour and sugar.
That's not actually a solution, though.
Oh, that's
It's a heterogeneous mixture. But a solution thoroughly mixed together on the particulate level. So brass, alloys. Alloys are examples of solid solutions. So stainless steel, 24-karat gold, pewter, brass, any of those are mixtures of metals. And you combine them as liquids, and then they when they solidify, yeah.
So it's not really a solution.
Whatever.
It is first.
Yeah. So yeah, it's hard to do with just smashing the two solids together. Yeah.
It could work.
It could work. Maybe
But
you should
would still
try
have
it.
to go to like,
Would that be pressure though?
yeah, then it would just go to a liquid.
Yeah, if you smashed them together hard enough, you could get them to melt, I suppose. Okay, so solubility. So you guys just have the greatest.
Like 2 M&Ms in your hand? Yeah, there you go. And then you
A
go like
solution
that,
of
like a red
M&Ms.
and a blue, and
Yeah.
and then you just wait a little bit,
A mess.
put it back, put your hand in the freezer.
Then you can make it a brown M&M.
You can make it a brown M&M, yes, because
Yeah,
the
we need
chocolate. So you pick out all the brown M&Ms when you eat M&Ms?
I prefer the blue ones.
The blue ones, not the green ones?
I think the brown ones are the best. It's like extra chocolate.
I don't think so.
Do green M&Ms still have a connotation?
What do you mean?
Never mind.
Dude, they don't have a different flavor.
They don't.
Solubility. So we can dissolve sodium chloride in water. So if you put a teaspoon of sodium chloride into a beaker of water and stir it up, it dissolves and it makes a solution. Right? And when that happens, the ions come apart from each other and they move around independently of each other. So when we dissolve ionic substances, they break up into individual cations and anions. Another way to describe that is to say that they ionize. Or dissociate, another big word. How does that work? Well, ionic substances, many of them are soluble in water because water is a polar molecule. So here we have the sodium chloride. The chlorides are the big green ones and the sodiums are the little gray ones. And then here we have our little water molecules. The water molecules are polar. They have a positive end on the hydrogen side and a negative end. And so the positive end is attracted to the negative ions. And the negative end is attracted to the positive ions. It's easy to get these mixed up. So the reason the ionic substance was a solid is because there are strong attractions between this +1 and -1 ion. And we've got attractions in this crystal that go throughout. So it's being attracted in 3 dimensions. And so these ions are not just going to suddenly give up those attractions. They have to be lured away. Okay, so here we have a sodium ion, and it's attracted electrostatically to these negative chloride ions. But here comes some water molecules. If you get enough water molecules around that sodium ion with their partial negative charges, they can replace that attraction that it had to the negative ions. And so the water molecules come and surround it, and they say, hey, come on, come out with us. And so they'll surround those ions and make them feel comfortable. And the water molecules can do the same to the anions because they just turn around and point their other end. They have a positive end and a negative end. Isn't that kind of cool? It's kind of cute, huh? It's like, come out and play with us. No, you don't have to stay with them. Come on. They're not luring them out for bad purposes or anything. They're just saying, come out and play. Pardon? Yeah, we're not talking about atomic creepers or anything. They have no negative, intentions toward these ions. They just want them to come out and socialize.
Just negative charges.
Just negative charges. Which are different than criminal charges. So that's solubility of ionic compounds. Solubility of polar substances. So here we have an illustration of ethanol. Ethanol is polar. We look at this molecule and we can see that it's not symmetrical, right? So it's got this OH over here. And in fact, we've got this hydrogen-oxygen bond in a polar molecule. This can do hydrogen bonding, right? So this hydrogen has a slightly positive charge, this oxygen slightly negative, while the water molecule is attracted to the positive charge here. And so it can interact in a strong way with the ethanol. Ethanol is soluble in water because of that polar OH bond. Another way to think of solubility is that water has very strong intermolecular forces for its size. It's got the dispersion forces, dipole forces, but it also has the hydrogen bonding. And so water molecules are real tight with each other. And in order for a liquid like ethanol to dissolve in the water, it has to be able to interact with the water and replace the interactions that have to be broken in order for the ethanol molecule to get in. Okay, so it's a little bit like, groups of people, and I don't know, I'll go with it anyway. Okay, so I'm of Swedish descent, so I can make fun of Swedes, and my husband's Japanese, so I can make fun of them. So say you had a big group of people, and you had Swedes that only spoke Swedish and Japanese that only spoke Japanese. And you've got, it's this big party with these two groups of people. Are they going to mix intimately and be thoroughly mixed up together?
Not unless your kids are sitting in the room.
Not unless my kids are sitting in the middle, yeah. But they don't speak Swedish or Japanese, so they'll be a separate clump unto themselves of the little brown children. This is what color they are. They've got brown skin and brown hair and brown eyes. They're beautiful. But the Swedish people are going to form clumps talking to each other because they understand each other. And a Japanese person is not going to go over there and be able to hang out long with them because they don't understand each other. He's going to go find other Japanese people to talk to because they understand him, right? So water has a very good understanding and very good interaction with the other water molecules. And so it's also a little bit like a click. So here you've got this other molecule wanting to come in and get into this crowd of water molecules. Well, if this speaks the same language that the water molecules do, it can probably get in. If it doesn't speak dipole forces and hydrogen bonding, it's not going to get in. Because the water molecules are so attracted to each other, they basically force other things out. It's a little bit, I forget which, I think it was the other class had this illustration in the book. I should put it in here, but I'll forget, and I won't. Anyway, so imagine marbles. Magnetic marbles and regular glass marbles. The magnetic marbles are going to clump together, aren't they? And they're going to exclude the glass marbles because the glass marbles have no attraction for the magnetic marbles. So in order for substances to dissolve in each other, in order for this polar substance to dissolve in water, it has to be polar. It has to have a way of being attracted to the water molecules. Does that make sense?
So with that whole, say if you looked at it as a family, that whole molecule would go with it and attach to water. It wouldn't break off.
No.
Which that would be an intramolecular force, but it wouldn't
Right.
break
If any of these bonds broke, we'd have a chemical reaction, and that's something completely different.
That's
This
the issue.
molecule is going to stay together. And so this is a small molecule. This is a small alcohol molecule. And so it's got this really nice polar bond here, and that interacts with the water. Now the rest of it just kind of sneaks along. There are other alcohols where there's a whole bunch more carbons out here. This is the nonpolar side of this molecule. If this gets longer and longer, then the alcohol is not soluble in water because there's too much of this part that doesn't interact with the water. So only the small alcohols are going to be soluble in water. Ones where you've got a whole bunch more of this nonpolar stuff are not going to dissolve.
What would be an example of that?
Like pentanol. Pentanol, it's got 5 carbon atoms, and on the end you've got the OH bond.
And what is that? Non-drinking?
Yeah, ethanol's the only one you can drink, and even that, it'll kill you if you drink too much. Of course, water will kill you if you drink too much too, right? Yeah. Here's sugar. What? What's sugar? That's sucrose, table sugar. It's a disaccharide. We've got fructose over here and glucose over there. Sugar's soluble in water. We know that, right? What do you see about this molecule that would suggest that it might be soluble in water? It's got all these OHs all over the place. There's one here, there's one there, and here, and over there. There's all these OHs. Okay, those are going to communicate really well with water. And so sugar is very soluble in water. You start getting rid of OHs, and you're going to lose your solubility. So it has to do with things that are alike, things that share the same kind of intermolecular forces.
So OH is an anion?
Do you hear your phone doing that?
Yeah.
Can you make it stop?
Well, if I went for it, that would be like admitting that it was me.
Well, right, but it's happened. And the first time was fine. But the third time, it's like, okay, this is going to be ongoing, so let's just take care of it already. So now you had a question. Do you still want to ask your question?
The OH?
Uh-huh.
So does it necessarily have to be the HO? Does it have to be hydrogen and oxygen? Or it could be... Well, because the hydrogen by itself won't...
Hydrogen,
differentiate.
the hydrogen by itself, the hydrogen bonded to carbon. Carbon and hydrogen are actually real close in electronegativity, and so this is essentially a nonpolar bond, so there's really not much polarity is there. Nice. I love this, Windows 8. Your battery is running low. You might want to plug in your PC. Okay.
And then once it gets to some,
Okay, we have power, but now we've lost our train of thought, so that question will remain unanswered forever. So let's talk about substances that are insoluble in water. I thought I got rid of all these transitions, but I did not, obviously. So oil does not dissolve in water, and we know that from personal experience, right?
yeah.
Oil is nonpolar. So here we have an illustration of an oil molecule. It's mostly carbons and hydrogens, and they tend to be very long molecules, and so there's just all this nonpolar business. So these guys have London dispersion forces, but they don't do dipole-dipole forces or hydrogen bonding. And here we have the water, and the water is busy with its hydrogen bonds, and we've got all this really strong interaction here. And so it's like those magnetic marbles. The water molecules are so tight with each other, they just won't allow anything to come in. So the water-water hydrogen bonds keep the water from mixing with the nonpolar molecules. So in order for a substance to dissolve, I could swear I got rid of all these transitions. In order for a substance to dissolve in water, you basically have to make a hole in the water. And to do that, you have to break the hydrogen bonds, those interactions between the water molecules. In order to do that, you have to replace them with something. It's like, okay, I'm depriving you of interacting with these other water molecules, so I'm going to interact with you myself instead, says the polar molecule coming in and dissolving in the water. The bottom line is this, that like dissolves like. Good grief. Come on. It's just, I swear life is out to get me sometimes. So like dissolves like. Two polar substances are likely to be soluble. Two nonpolar substances are likely to be soluble. Polar and nonpolar, not going to happen. Any questions?
So if oil is not, what would dissolve? A gas?
No. Another nonpolar substance. Two different oils will mix together just fine.
Oh.
Oil and gasoline would probably work. I don't recommend trying that, but
Well, that's what you get, certain fuels for, like gas blowers and
yeah,
that combination.
you have to mix the gas with the oil.
And it has to mix, so that
Right.
would be a solution.
Yeah, and they'll mix together just fine because gasoline is also nonpolar.
Okay.
And you don't want water in your gas tank because the water and the gasoline don't mix, and the water is less dense, and it goes to the bottom of your tank, which is generally where the intake to your engine is, and then you get water in your engine, and it doesn't burn real well. It just doesn't. So here's concept check. Which of the following solutes will generally not dissolve in the specified solvent? Choose the best answer. Assume that all of the compounds are in the liquid state. So CCl4 mixed with water. CCl4, is this going to be polar or nonpolar?
There's gonna be some.
Okay, so a carbon-chlorine bond is polar, but is the molecule polar? Are there any lone pairs? No. Are all the atoms bonded to the middle atom the same? Yes, they're the same.
Oh, they.
So this is nonpolar. Does a nonpolar substance dissolve in water? No. So this one is not going to dissolve.
What is that?
What is what? CCl4, carbon tetrachloride. It's an organic solvent. It's not some. It's pretty toxic. So ammonia, NH3 mixed with water. Is that going to mix? Well, we have to think about, is ammonia polar or nonpolar?
Polar.
It's polar. It's got lone pairs. It's lopsided. I showed you the model earlier. So is polar ammonia going to mix with water? Yes. And we're looking for ones that will not dissolve. How about ethanol and water? Just looking at this, CH3OH, does that look like it's going to be polar? Yeah. This is polar. Will it mix with water? Yes, it will. How about nitrogen mixed with methane? Is nitrogen N2, is that polar? No. Is CH4 polar? No. Nonpolar and nonpolar, will those mix? Yes, they will. So the first one is the only one that will not dissolve. So when predicting if things will dissolve or not, you have to look at, are they polar or nonpolar?
What was the methane?
Methane and nitrogen,
What is the methane?
they're both nonpolar.
No, but what's the formula?
CH4. So we're going to just continue on here because we need some of these concepts for lab today. So things are not infinitely soluble. The solubility of a solute is limited. So if you take a glass of water and you add a teaspoon of salt and you stir it, it'll dissolve. If you keep doing that, you'll eventually get to a point where no matter how long you stir it, more salt will not dissolve. That's called a saturated solution. The solution, the solvent, is holding as much solvent as it possibly can. There's no room. You think of a sponge being saturated with water. It's full. So when a solution is saturated and you add more solute, it will not dissolve. An unsaturated solution has not yet reached that limit, and if you add a little bit more, it will dissolve. So saturated and unsaturated. And then there's supersaturated. A supersaturated solution contains more dissolved solid than a saturated solution. I was expecting him to say, what? So that's not possible, is it? How can it hold more than it can hold? Well, it happens by making a solution that is saturated at a higher temperature, an elevated temperature. Because solubility depends on the temperature. For most things, solubility increases with temperature. So hot water can hold more solute than cold water. So you can make a solution at a higher temperature and make it saturated, and then if you let it cool down without disturbing it, it may remain in solution. but that's not stable. It's an unstable solution, and so if you add a crystal, or sometimes if you just bump it, all that salt will precipitate out. And I'm going to do an example of that in class today. It's pretty cool. Supersaturation.
Would that be like in making candy? Like if you're going to add more sugar to candy, you would have a higher, I'm sorry, not related to food, where you have a certain amount of sugar you have to add, but only a certain amount dissolves at a time, and you have to keep.
Yeah, and the reason that you heat it is the solubility increases as you heat it. So solutions are mixtures. The amount of the substances can vary, and so we need to specify the amounts, the relative amounts. And we're interested in the relationship between the amount of solvent and the amount of solute. There are qualitative measures which do not involve numbers. And so we can say it's concentrated or it's dilute. And those are relative terms. Concentrated means there's a relatively large amount of solute. Dilute means a relatively small amount. So a dilute solution is going to have more solvent than the concentrated solution, or less solute if it has the same amount.
So concentrated would be like your frozen orange juice, and dilute would be what you buy in the mix.
Right. And yeah, so you buy frozen concentrate of orange juice, and it's like, well, it's frozen, but if you let it melt, it is a liquid. But it's way too concentrated to drink, right? So you need to dilute it, and you add water to it, and when it's diluted, then it's appropriate to drink. So there are different ways. Oh my goodness, I need to stop here just a minute.